So I think we'll start today's lecture by reviewing what we have done about the last lectures. So in our last lecture, basically, we introduced two relatively simple examples. One is the 1D random walk. That is basically you can either step forward or backward in a random fashion. And then we ask the question, after you perform n steps, then you will be in some position, and what is the distance between your final position after n steps and the origin? And what we found is that it can be characterized by a quantity, which is the root mean square of our displacement vector, which will be proportional to or equal to square root of n. Okay, so that's like the 1D simple example, and we can show that by mathematical induction. Okay, so another very similar example is the 2D random walk. So in this 2D random walk situation, we have a very similar setting, but instead of moving forwards or backwards, we actually allow our system or allow the Drunkard to move in arbitrary direction, but with the restriction that each step size is a fixed value, okay? So fixed step size, but the Drunkard can choose arbitrary random direction, okay? And what we found is that it seems like we made some modification going from 1D to 2D. But what we found is that the root mean square of this displacement vector actually share very similar behavior, that it also has the square root n behavior. And here we just assume that the step size is said to be 1. So they just basically all equal to, in these two examples, the root mean squares are all equal to square root of n. Okay. So now, once we introduce these two examples, then we say there are some very interesting behavior for these systems. The two very interesting behaviors that we mentioned is the scale invariance, which just means that when the step number n is large enough, actually the statistical behavior for different n, for example, if n1 and n2 are both large, and though n1 and n2 are two numbers that characterize two different systems. One is with step number n1, and the other is with step number n2. So in principle, it is not guaranteed that when you change the step number, they have the same behavior. But in these two examples, we can show that when n1 and n2 is large enough, even though they are different, the root mean square behavior is actually identical. They share the same functional form. They are proportional with the square root of the step number. So it's square root of n1 and square root of n2. And that's the concept of scale invariance. Okay. And another very important idea is the idea of universality class. So this idea basically links two different systems. One is the one-dimensional random walk, and the other is the two-dimensional random walk. And they both share the square root n behavior, which suggests that there are some fundamental mechanism between them that are important, such that both of them basically give you the root mean square to grow proportional with the square root of n. So this idea of universality class is in these two systems seems to be trivial, because you can solve everything in these two systems. However, the idea is actually much more general. It can actually connect to two very different systems. For example, one of the famous universality class behavior is the phase transition between liquid and gas phase. And this phase transition actually can be understood if you understood it in terms of the idea of universality class. Actually, this phase transition is belongs to the same universality class with the magnetic system, which is the Ising model. So basically, the two systems are very different. One is magnets, and the other is water and gas, but they still have very similar critical behavior. But we are not going to discuss it right now. I just want to give you a flavor about what does this important idea mean. So, okay, so after that, in the discussion of universality class, we kind of suggest that some of the detail of our system is not really important because they might not modify the scaling behavior of your system. For example, in this 1D random walk, whether you are moving forward or backward, or you are moving in arbitrary direction in a continuous fashion, actually are the difference between these two systems, but they did not change the scaling behavior of the system. So in that sense, those details are irrelevant details. But we also give an example where some of the details will be important, and that example is the polymer physics, where if you try to understand the direction of your monomer as some kind of random steps, then in the polymer physics, there is a constraint that the polymers cannot overlap with each other because polymer occupies some volume. So that condition will lead to the self-avoiding condition. And naively, we think that maybe it is not really important and it will not change your understanding. But as we discussed in the last lecture, it actually modified the scaling behavior from square root of n to n to some other power, depends on what is the dimension of your system. Okay, so in the discussion of this universality class idea, we introduce relevant couplings. Okay, so we just discussed this idea from the qualitative point of view instead of the quantitative point of view. If you want to understand those ideas in a more quantitative picture, you probably need to learn more theoretical tools such as the renormalization group idea, which might be covered in the statistical mechanics 2 or later in this semester. It depends on how things goes. Okay, so I think that's the very quick review about what we have done in our last lecture. So are there any questions so far? Okay, so if not, let's try to think a little bit further about what we have learned and try to question some to question ourselves about some of the physics. So if we try to understand this universality class idea from the two 1D random walk example and the 2D random walk example, we can try, if we try to find out our node, then we'll find that one of the important idea in the 1D derivation is that we have this quantity, the average quantity of your displacement vector and the random step at the next step, or in this notation, the S step needs to be 0, okay? And in the 2D random walk example, basically very similar quantity appears, but now it becomes a vector instead of a scalar. And we say that the expectation value is 0 because the next random step can be chosen in an arbitrary direction and there's no bias, okay? So that's basically the two crucial idea when we try to derive the square root and behavior of our mean square. So that's one condition that's very important. And the other condition is that when we are trying to do the mathematical proof, these two systems also has the condition that the step size is fixed. So basically, in the 1D case, you move forward or move backward by 1 unit. And in the 2D case, you basically choose the size of your vector to be 1, but you can orient it in different direction. Okay, so now we can try to ask ourselves, if we try to think along the universality class idea, we mentioned that, oh, maybe there's a special mechanism behind these two examples such that they both share similar behavior. So maybe this relation or the fixed step size actually is the important ingredient in order to have this square root and behavior in your mean square. So we'll try to check whether we can push our understanding a little bit further by considering the case where we allow the step size to be a variable. Now it is no longer just unit 1. Maybe you can move a little bit. You can have a bigger step or a smaller step. So basically, it means that in the drunkard's walk, it means that this guy is so drunk that he cannot even maintain the step size of his footsteps. Okay, so that's what we are going to do now. And it turns out that this fixed, once we relax this fixed step size constraint, actually, we need to make some approximation in order to proceed. But this approximation actually is very valuable for us because it can give us the connection, or at least show how we can connect from a microscopic understanding to a macroscopic description. And in this case, the macroscopic description actually corresponds to the diffusion equation, which is a dynamical equation that describes how a density profile diffuse in your system, and the way it diffuse is actually assumed to be just like a random walk process. Okay, so let me just write down what I'm trying to say. So let's try to use the variable r to denote the case where the random step size can change its magnitude. Okay, so let me just write down the microscopic condition for our system. Okay, so this is the microscopic picture. Okay, so this is this r is basically the position of our particle at the position t plus t. Okay. So here I use the quote time because to some extent, the important thing is not about the nature that it evolves in time. The important thing is that we try to, have a system that to start with, and we try to grab the information by, taking photos about our system's configuration. And when we take our photo, we might take our photo at time t, and after some small time difference, we take another photo, then we have our information at time t plus delta t. So the left-hand side is basically the position of the particle at the time where we take our photo at time t plus delta t. Okay, and the first term on our right-hand side of the equation is actually the position at time t. Okay, and the last term is actually the random step Okay, so if I draw it, what does that mean? It means that maybe my particle is at some position r at the time t. Okay, then at that point, what is the the next position of my particle is basically determined by the random value L. So this L can be a very big number, maybe LT. When LT is large, that just means that after the time t, we go to the time t plus delta t, then the position will be at somewhere nice, very far away. Okay, and this L could be very large or it can be very small. So if it is a very tiny L, for example, if it is very small somewhere, also it can move in the opposite way because we don't specify what is the direction of this L. So if it is moving in the opposite way and it is a relatively small random value, then R of t plus delta t will be in some other place. Okay, so if we try to use that language to describe the microscopic motion, then the particle will just move one step further, and maybe you will choose another random number. You will choose a little bit further, moving a little bit further away, or you can move backwards in some different values. Okay, so this is basically the very simple idea about this microscopic process. And for our purpose, actually, you can also try to think of it in terms of some discrete values. For example, you can think of it as some kind of Rn, basically equals to Rn minus 1 plus a random value Ln minus 1. So that's roughly if you try to discretize this expression. Okay, so that's basically the setting. So are there any questions so far? Yes, please. Yes. Okay, so that's a very good question. So that's why I mentioned at the very beginning that we are trying to take the, imagine this process as you try to take a photo of some randomly, jiggering around particles. So in reality, of course, everything will move in a continuous fashion unless you are talking about some quantum mechanical stuff that is just eternal. But here we are talking about some classical particles. Okay. So in principle, this t and delta t are all continuous variable. So you can choose your delta t to be arbitrarily small or like a gigantic value. Okay. So the key question is like, what is the typical time scale for your system? Okay. So at this moment, when we are trying to discuss the microscopic picture, you can think of the particle as like at a finite temperature, they will just like move very quickly or randomly. So in that sense, this delta t should be considered as the microscopic time scale. So we can compare that with the macroscopic time scale. What do we mean by that? It means that when we are trying to look at our system, maybe a cup of water or something, and we want to understand whether this cup of water is changing as a function of time, then the time scale that human being can sense maybe is about, seconds or something. So that's like the typical time scale at the macroscopic world. But at the microscopic world, the time scale could be much shorter. It could be like microseconds or something, because they are just, moving around really fast. Okay. So, but at this moment, at least this mathematical model, we are talking about the microscopic time scale t. And then later, we'll try to derive the equation that we try to understand how this kind of little particles that move in the microscopic time scale will give us some understanding about our macroscopic world and how to describe the macroscopic behavior for our system. Okay, so that's basically the logic. And at this point, we are just trying to specify what these particles are doing at the microscopic time and then scale. Okay, so are there any other questions? Okay, good. So let's see. Okay, so here one thing that is not obvious is about this L. Here we just say that it is a random number, but this is basically a assumption. So because you can think in the following way. So suppose I have a particle, right? We have Newtonian mechanics. So usually how we predict what is the position of our particle in the next time step is that we just figure out what is the force of that apply on this specific particle, and then we use the Newton's second law, and we got the acceleration, and then we can make a linear extrapolation, and we know where the particle will be after some small time step delta t. But here, why do we choose this random step is because if we try to understand the macroscopic number of degrees of freedom, usually the force is just so complicated. So maybe interact with its neighbor, but the neighbor of this reference particle might have 10,000 or something nearby. Then it will be really complicated to analyze this problem from the first principle. So here we are trying to make an assumption that maybe the environment will basically bombard this reference particle in a very chaotic way, such that the behavior for this particle at the next time step is basically a random number. So that's like the gist of this idea, like why we model our system in this way. Okay, we kind of abandon the fact that we want to analyze the force that apply on this particle because the system is just too complicated. So we just assume that it is a random value, at least for the next step. Okay. Okay, good. So in order to be more specific about, or at least in order to move forward, we'll need to make some assumption about these random steps. Okay. So let me just write down the properties of or like how to characterize this random number. So usually when we try to characterize the random number, the most important quantity is the probability distribution function. Okay. Okay, so let's denote this probability distribution function as chi, and the variable of this probability distribution function is the step size L. Okay, so what does that mean? If I just randomly draw a figure, for example, let me just draw it slowly. Maybe if this is the chi of L of our system, what does that mean? It just means that this function basically gives us the probability for this particular step size. For example, if we try to ask what is the probability to have a step size L1 for this random number, basically what you need to do is that you just take out this probability distribution function chi at L1 and make an infinitesimal integral. DL. Okay, so basically that's a small stripe, like in what you have learned in the calculus about this kind of Riemann sum stuff. Okay, so why it is important? Because once you know the probability distribution function, actually you know basically everything. You can evaluate the average value, you can evaluate the variance and all other things. Okay, but here we just try to formally express the probability distribution function chi of L, and then we do things in a backwards fashion. So usually you got a probability distribution function, then you evaluate the average value, you evaluate the variance, but now we are going to do it in opposite way. We assume that the probability distribution function has specific average value, and we assume that it has some specific variance, and then we start from there and try to see, like what kind of conclusion we can get. The reason that we want to do that is because we want to keep the probability distribution function to be a very general input, that we don't need to specify what is the detailed form of our distribution function. It can be like a Gaussian function, or it can be like a block distribution or anything. So for example, you can also have some probability distribution function that looks like a like a hat or something. Okay. But anyway, so just let me try to write down what do I mean by that. So we assume okay. The first thing is that we assume that if we wait, I should change my notation. Okay, so if we have this probability distribution function to be chi, we require the integral of this chi over all the possible values to be 1. So that is just the normalization condition for a probability distribution function. Okay, so naively, it seems like it is a very intuitive assumption. Of course, it needs to be like so, but there's some physical meaning about this constraint. It just means that your particle cannot disappear in the vacuum. Okay, so most of the time we don't consider that kind of situation. For example, in the water molecule, you just move around, it will not disappear. But sometimes if you are discussing about some particles such as photons, they can be absorbed by the environment or things like that, then the probability will not be conserved. So here, this seems quite trivial assumption actually suggests that these particles cannot disappear in our in the discussion later. Okay. And the second condition that we would like to have is the constraint about the mean value to be 0. Okay. So it just means that it just means the expectation value of the random steps basically are 0. Okay. So so in principle, this is not super important, but we'll just take that because it simplifies a lot of the calculation and make our life easier. Okay. And the third constraint is about the variance, or about the second moment of this distribution function. let's parameterize this second moment using the parameter a squared. Okay, and the physical meaning of that is basically the width of the distribution function is about, or at least at the order of this parameter a. Okay, so okay, so what does that mean? It just means like, you know, suppose we have some kind of distribution function. Maybe it looks like some kind of Gaussian, and the width of this distribution is basically of the length scale of a. Okay, or if it is a block distribution, then this length scale is proportional with a. Okay, so of course you can think of various different kind of distribution function that satisfy this condition, but we'll see that actually those the difference of these distribution functions actually is not very important when we try to derive our effective theory or the macroscopic theory. Okay, so are there any questions so far? Yes? Okay, so you mean like if I have a probability distribution, something that looks like this, I don't know, maybe give it some constant k, or proportional to this thing, and will that satisfy this criteria? Is it the question you're asking, or like how to understand? So the question is, if you have a distribution function that looks like this, can you define a quantity like this variance, or like the average of the z square, right? So in principle, the answer is yes, because what you need to do is that, of course, another thing, when you discuss your distribution function of this object, right? We can think, one step by one step. The first thing is that it needs to be normalizable. So it means like integrate over some possible value of L, it needs to be 1, right? So you can immediately see that if I try to draw it, it will basically looks like this, right? And if I allow my L to go from positive value to the negative infinite, then I will have problem, because I will never be able to satisfy the first condition, because it just diverges somewhere. It just becomes very large. So when you try to integrate it over, it will not be a simple value, so you are not able to normalize it. So in order to do that, actually, you can say something like, okay, so in order to make my distribution function satisfy the condition, maybe you can put a cutoff somewhere here, lambda. Then if it is the case, then the integration of the first constraint is basically counting what's the volume here. Then once you do the integral, you will have some function that is a function of this lambda. Then you can use that to normalize your probability distribution function. So let's formally write it in this way. Let's just say lambda to infinite PL DL. Then this thing will be some function as a function of lambda, right? Then the true probability for this distribution function should be f of lambda times exponential minus over k in this case, because once you do the integration, then automatically you'll get 1, such that it satisfies the normalization condition. Okay. So once you have this, function form for your, yes, question?
Why we consider the two conditions fixed variance?
Oh, the question is about the purpose of these two. Good question. The second condition is just saying that we want to simplify our calculation, and you'll see why the second condition is not super important a bit later. And the third condition is actually trying to say that you have a distribution, but you want to have some feeling about what is the width of this distribution of your random number. Okay, but let me try to get back to the previous question. So once you have this probability of L, then how to evaluate this quantity is just, a matter of technical detail, because you can just evaluate this integral, something like z squared pz z, but now you need a cutoff from lambda to infinite. Then you will, once you evaluate it, you will get some number. Okay, so the question is why we want this condition and this condition. So as I mentioned, short answer is that the condition 2 is just for simplification. When we try to derive what we are going to get, it will be easier to get the important points of this derivation. But of course, there's another very important idea, is that we are trying to make connection with the random walks. So random walks, in the previous simple 1D and 2D example, we know that the expectation value of your displacement vector needs to be 0, right? Because it's equal likely that you move forwards or you move backwards. And it is equal likely for you to move in the 45 degrees and for you to move in the 37 degrees. So those conditions, if you try to pack them in the this language of distribution function, actually correspond to the second condition, that the average of this random move will basically be 0. Okay. Yes. Yes.
So
yes. Yes, like if you are thinking about this kind of situation, then this condition might not hold. Then when you are trying to derive the microscopic modeling, then you need to impose other condition instead of this one. Yeah. So, okay, so that's another important point. Okay, so I think, where am I? Okay, so now we basically define our microscopic models, and next we are going to ask a question about how to connect this microscopic understanding to our macroscopic world. Okay, so let me just try to draw something. Suppose we are in a one-dimensional system. Okay, so we have a bunch of particles, maybe somewhere here, and I'm just trying to randomly draw some particles. So you can immediately see that there are some part of the space has a dense particles. There are more particles somewhere nearby here, and then there are fewer particle or dilute particle somewhere further away from this center. So if I try to think of the distribution of these particles as in the macroscopic world, of course there will be tons of these little particles that I'm not able to draw. But if we try to think of it in a continuous fashion, then basically we can try to describe the density profile of those particles by some kind of density distribution function. Let me try to denote it by rho, and it will be a function of your space And in principle, it can evolve in time, so it will also be a function of time. Okay. So I think it is about time to stop here. I will try to continue the discussion in the next lecture after 10 minutes. So let me just try to say a little bit more about what we are trying to do. So here we are trying to say that this is what happened in macroscopic world, because there's no way for we to identify where is the hydrogen molecular or the water molecular. So we try to use a continuous function to describe it. And then we try to make a connection between what we just proposed, that basically these little particles will move in a random way, and try to go from this microscopic picture to connect to the density profile, which is described by a continuous function. That is more reasonable for our macroscopic world. Okay, so I'll stop here, and if you have any questions, just ask me. Okay, so I think we will continue the discussion. So basically, we want to have a macroscopic description if we understand that our particle is distributed in space in certain way. Okay, then we want to ask the question, like, suppose we have our particles described by this density distribution function, and we also know microscopically those particles will move in a random fashion that we just described previously using this probability distribution function chi of L. Then we ask how this density profile rho of xt evolve as a function of time. Okay, so that's basically the question that we are trying to ask. So let me try to describe things in a more pictorial way. So suppose at some time t, we have our coordinate labeled by x sub t. Okay. So initially we might have some, profile like that. Okay. And then after some time, maybe I should change the color. Oops. Okay. After some time, it will be. Okay, so let me try to write down the parameters more explicitly. Then maybe the distribution function will change as you will, I don't know, diffuse in a sense that some of the weight at the center will be redistributed in other places. Okay, and this coordinate that's down here is the time. So basically, you can think of it like, at the initial time that's described by this blue coordinate, actually you got some kind of profile, and after some time you got this green profile, and the shape of your density basically changes. And naively, I think even before we do any calculation, we will expect that when the time is very, very long, like after we release our particles after a long time, the system supposed to become very, like basically every particle will have very even probability to distribute in the space. But I didn't write. My hand just shakes, so maybe I should try to use this more technique. Okay, now it is a straight line. Okay, so basically it just means that after a very long time, the particles will supposed to distribute evenly. At least that's our guess. Okay. So the question that we are trying to ask is how to understand like the evolution of this profile to going from this step to this green step. And as a function of time, then we know like how a density profile changes as a function of time. And the assumption or the input that we use is basically the microscopic model we have in mind. Okay, so in order to make the derivation a bit more simple, I'll just call this coordinate t prime, no t prime, x prime, and this green coordinate, I'll just call it x. Then I'll try to write down the equation or like the question that we want to ask in a formal way. That's basically we have some density profile that is x prime described by x prime t, and we want to ask how does it go to the next step that's basically described by the coordinate x at time t plus delta t. So that's basically the question that we are trying to ask. And here, the input is microscopic model. Okay. So let's start. So the first thing we would like to describe is what is the right-hand side of this relation when we assume that the random steps that we are taking is described by the probability distribution function chi. So basically, you will look like this. Okay, so let me try to describe what is the meaning of this expression. So basically, the left-hand side is trying to ask what is this value when we choose it to be a specific position x. Okay. And from the microscopic picture, we know that in order for our particle to end at this particular position x, basically what one needs to have is that suppose, let me try to draw a dashed line to represent the relation with the previous coordinate. Okay, so in order for our particle to move to this position x at time t plus delta t, what that means is actually we might have some particles that sitting somewhere here. Okay, let's suppose it to be denoted by x prime. Okay, and this particle needs to take a very particular step size of the random variable in order to move to the position x at the next step. So the particular step size it needs to take is basically this segment, and this segment is basically you can just denote it by x minus x prime, right? Does it make sense? Okay, so why do I want to specify this relation? The reason is because in order for our particle to end up at this position x, actually you have various different kind of possibility to go from your original position to this final position x. And the various probability actually is characterized by this probability distribution function of your system. So once you are able to make this connection, then you are able to use the condition that we assumed for the probability distribution function to describe this dynamical process. Okay. So that's the idea. So if you look at this expression, actually, this term is actually saying that we want to know what is the height. Basically, let me use different colors to express what this is. So this term is basically the density of your density profile at the coordinate x prime at time t. So basically, it is the value of this height of this function rho of x prime t. Okay, and then this density will need to multiply the probability that it will move to the correct position, and this probability is basically characterized by this quantity, which is the probability distribution function times the little delta x prime. As I just mentioned, that this is just something like the Riemann sum you have learned in the calculus course. Okay. So why do you need to have these two? Because once you integrate or you sum over all the possible value of your x prime value, then you will get the final density that the particle could end up at the specific position of x. That's basically this term. Okay, so what does this mean? It's simply, these particles can move here, and there are also some other particles might sitting somewhere here, but eventually you will move to this particular place x. Okay, so I'll just remove some of the lines in order to make the figure more readable. Okay, so are there any questions for this equation? I'll just write down the meaning of the right-hand side.